Welcome back. Looks like we're just about done with things here. We're entering into section 5.4. We'll do this section. We'll do 5.5. I had hoped we'll get 6.1, but I don't think that's probably going to happen, which is sort of nice. We end up on one of my favorite topics on harmonic motion, where you get resonance phenomena, which is sort of a fun application of differential equations. What we do in section 5.4 here is that we're going to add a forcing term. So rather than just letting go of the spring and letting it slowly go back to equilibrium, we're going to actually put some type of a motor onto the spring or something like that to keep it going. Now, we're not going to want a constant force because that'd be pretty boring and just move the equilibrium. So we want a harmonic, an oscillating force of some type acting on it. So we have our mx double prime plus ax prime plus kx, but rather than putting equal to 0, we're going to have that be equal to some f1 cosine of omega t, where f1 would be the magnitude of this trigonometric wave force we're putting into it. Okay, as usual, to make it fit our notation, we divide through by m. So when we divide through by m, we get a over 2, which we defined, sorry, a over m, which is 2b, the way we define b. We take lambda squared to be k over m. And we define this new variable E1 to simply be the F1 magnitude divided by the mass. And that sort of makes sense that if you have a really massive object, the force is not going to have nearly as much effect on it as a lighter one. Okay. Now, for this argument, we're going to look at being the underdamped case. I will do one example when I publish the examples that is in the critically damped case. The process works the same, but the interesting one is when things are underdamped. And so that's where we're going to develop all of our formulas. And really, to be honest, in the overdamped case, the algebra is pretty easy. Okay, since it's in the underdamped case, we get our complementary solution here. E to the minus bt, and then we get a C1 sine of lambda squared minus b squared times t, and a C2 times cosine lambda squared minus b squared times t. Notice, over time, though, this is going to die out because of this exponential decay term out there. Our particular solution would be done by undetermined coefficients. And so we're going to A cosine omega t and B sine of omega t. We don't have to worry about these overlapping with the complementary solution because the complementary solution has this exponential decay term on it. So there's no worry about having to do an adjusted UC set. And again, an important thing to recognize here is as t goes to infinity, x sub c goes to 0. And that's important to note because what it says is as time goes on, the only thing that really will survive is a particular solution. So regardless of the initial conditions, it will eventually settle down into the exact same function, which will be determined by this particular solution. Okay, so we're really interested in what the A and B are. Now, again, in this underdamped case, you can just set up the solutions, take the derivatives, take the second derivative, plug them in, and you can get formulas for A and B in that case. The book goes through all the algebra, but to be honest, it's not terribly instructive, just algebra. So when we go through and we solve that, you get A is E1 lambda squared minus omega squared. And then your denominator is lambda squared minus omega squared, quantity squared, plus 4b squared omega squared. A lot of messiness here. Main thing to notice is that the denominator of A and B are the same. Okay, so 2b omega E1 is the numerator for capital B. Okay, now I would notice, and you'll see in the examples, if we're not in the underdamped case or the function over here is a sine function or some other trig function, then you're going to have to go back to undetermined coefficients, just do it the usual way. It's not terribly hard, it's just a little bit of tedious algebra. But what I'm really interested in here, and what we're going to use in the next section, is the amplitude of this particular solution. And if you remember, for a trig function, when you have a cosine omega t plus b sine omega t, the amplitude of that motion becomes the square root of a squared plus b squared. Okay. Well, if we do that, we take a squared, we take b squared. Notice, since the denominators are the same, I just put the denominator squared and put as a common denominator. I factor the e1 squared out of the numerator, and what I'm left with, notice, is the same thing in the denominator to the first power. So I have the first power of this messy expression over the second power of this messy expression. And of course, everything's inside the square root. So I can reduce that, and I just get the first power of the messy expression and its square root. The square root of e1 squared is just e1. Now, this is going to be important in the next section, because lambda is fixed. You know, the mass isn't going to change on us, and the spring isn't going to change on us. Omega is something we can control, and generally the friction isn't something you can adjust either. So the thing that we can adjust here is this omega. That's the frequency, that's related to the frequency of the thing that we're putting in. The period would be 2 pi over omega. The frequency would be omega over 2 pi. So as we increase omega, we're increasing the frequency of what we're putting into this system. And notice, by changing the frequency, we're actually going to change the amplitude of the particular solution. The complementary solution is going to die out, as we've seen. Let me adjust my camera so you can see that fully. So the complementary part is going to die out. We're going to be left with this particular solution that has this amplitude. If we change omega, it's going to change the particular solution and change its amplitude, which is an interesting thing, because we're not changing the F1. We're not changing this amplitude of the input, but changing the frequency will change the amplitude of the output, which is a very interesting phenomena. And that's what causes resonance at times. You can get something where the amplitude of the output here far, far, far exceeds the value of the input amplitude. And that's going to be an interesting one. I will also be posting a video in section 5.5 just before we put up the video for the lecture. And that's going to be a video on the Millennium Bridge in London. It was built about 20 years ago, right at the Millennium. And it did some crazy things. Thankfully, nobody was hurt, but it did do some crazy things, and it really gets into the whole idea of resonance phenomena and what value of omega here actually makes this a maximum. So we're going to do some Calc 1 and maximize that function as a function of omega, and then ask, okay, what does that mean in terms of how do you get resonance to occur? What are the conditions necessary for it to occur? But that will have to wait for section 5.5. I will post a couple of examples. In this section, the examples are probably more important than the video, so you probably want to read through them. I'll have one where the formulas apply straight out, and I'll have one example where it doesn't quite fit the description. It'll be a case of something being critically damped. And in that case, you just have to go back to first principles for undetermined coefficients. Well, take care and stay healthy, and look forward to next time.